The next little section here is about moments and center of mass. So our goal is to find the center of a thin plate where we could balance it on an object. So the point is called the center of gravity or center of mass for the plate. So first we consider a simpler situation where you have something like a rod sitting on a fulcrum. So let's look at my rod, and this isn't of negligible weight, but it's what I could find. So if I take my ruler and I can sit it here on my, let's scroll out, I can sit it here on my sideways eraser, and you can see that it balances when it's exactly in the center at 6 inches. But what happens if I want to balance this ruler with a quarter on one end and a penny on the other? Well, the quarter goes down just like if you have a bigger kid and a littler kid. So if you're on the teeter-totter and you have a big kid and a little kid, what do? Well, the big kid has to get closer to the fulcrum, and the little kid has to get further away from the fulcrum. So let's see if I can balance it. Oh, look, I got it to balance. So I had to move it over so that the fulcrum is closer to the heavier weight. So shorter distance goes with the heavier weight. The longer distance goes with the lighter weight. I have taken my little masses and I put them here along the x-axis. So I put x1 right here and x2 right here. So x bar is the center. So the distance from here to here is d1, the distance from here to here is d2. So that means that d1 is equal to x bar minus x of 1. Distance 2 is equal to x of 2 minus x bar. And we know from the rod will balance when m1 times d1 is equal to m2 times d2, thanks to Archimedes. That means that m1 times d1 equals m2 times d2, m1 times x bar minus x1 equals mass 2 times x of 2 minus x bar. So now I'm going to see if I can get x bar all by itself. So m1 x bar minus m1 x1 equals m2 x2 minus m2 x bar. Well, let's get everything with x bar on one side, so I'll leave it over here with m1 x bar plus m2 x bar is equal to m2 x2 plus m1 x1. So m1 plus m2 times x bar is equal to m1, and I'm just going to put them in numerical order because it pleases me. m2 x2, so x bar is equal to x1 plus x2 times, can't factor that out because they are different. We have m1 x1 plus m2 x2 all of that over m1 plus m2. So, mass times distance for object number 1 plus mass times distance for object number 2 divided by the total mass. With x1 and x2. Okay, so the numbers m1, x1, and m2, x2 are called the moments of the masses with respect to the origin. It says that the center of mass, x bar, is obtained by adding the moments of the masses and dividing by the total mass. So the moments are just a measure of how much the object wants to spin around the origin, how much it wants to be off balance. So the center of mass is obtained by adding the moments of the masses and dividing by the total mass. If we have a lot of objects all around, we can add them up and divide by the total mass. So we add up all the moments, divide by the total mass. That gives us the center of the system. So starting with just the sum of the moments gives you the moment of the system. So, moments, centers of mass. So if we want the moment, which is the tendency of the system to revolve around the y-axis, the moment of the system about the y-axis, you take the mass of the object times its x-coordinate. So I kind of think of it this way. You're on the x-axis, you get your x-coordinates. That is your tendency to flip in the y direction. You take the masses and the y-coordinates, and that's your tendency to move in the x direction. So let's look at an example. And I'm going to take a minute and plot these points. I plotted my points and I labeled them with their masses. So first I want to calculate the moments. So let's find m sub y. So that would be my tendency to move about the y-axis. That means I do the mass times the x-coordinate plus the mass times the x-coordinate plus the mass times the x-coordinate. So minus 3 plus 8 gives me 5. 5 plus 24 is 29. And then the moment around the x-axis, so my tendency to flip in the x direction, I take 3 times my y-coordinate plus 4 times my y-coordinate plus 8 times my y-coordinate. 3 minus 4 is minus 1 plus 16 gives me 15. Now I need my total mass, which is 3 plus 4 plus 8. So 7 plus 8 is 15. So x bar is m sub y over m. So 29 over 15. And y bar is m sub x over the total mass, which is 15 over 15, which is 1. So I'm going to go to the pretty picture so that you can see where it's more in scale, that it really does kind of look like the center, not exactly what the center of the area is because the masses are different. That's where you would have to locate your point that you wanted to balance that center, those objects on. So now we're going to go from just little points to a plate. So imagine trying to balance a plate on your finger. You may have tried that, or a basketball. But we're going to go with a flat plate of uniform density rho that occupies a region in the plane. And our goal is to find the center of mass, which is known as the centroid, x bar and y bar. In doing so, we use the symmetry principle, which says that if it's symmetric on both sides of a line, then the center of gravity is going to live on that line. Makes sense. Rectangles balance right in the middle. So we take our region, we divide it up into strips. There's our strips. And we look at the center there. So each center has an x coordinate and a y coordinate. The x coordinate of your center is always going to live halfway between the two endpoints of the center. So your x coordinate of your center is equal to x sub I plus 1 plus x sub I divided by 2. So it's really just x sub I plus x sub I minus 1 over 2. The average between those two. The y coordinate is going to be half of f of x sub I. So, center of the ith rectangle. And this is the y coordinate of the center of the ith rectangle. Now I want to find the moment with respect to y, the tendency to revolve about the y-axis. That involves the x coordinates. And we know up here we would take the mass times the x coordinate. So my x coordinate is x bar. And the mass of this little ith strip is going to be length, or the height of the strip, times the width of the strip. The height of the strip would be f of x bar, and the width is my delta x. The moment about the x-axis is going to be the y-coordinate, which is 1/2 of f of x bar times f of x bar delta x. So this one's 1/2 of f of x sub I. I left out my sub i's. Because I'm going to add them all up. So let me add a sigma here. And m sub x is equal to the sum of all of these. X is equal to the sum of the x sub i's. And now we'll square this times delta x. Okay. Hopefully I made it through that okay. So we add up the x coordinate, and then this is the mass. We add up the y coordinate of the center of the strip, and this is the mass of that strip. Now you can see where we're going. We let the number of rectangles go to infinity, and we end up with a couple of integrals. And I'm just going to come on down here and show you. And I left out the row because we need to have row for the density of the object. So the moments have rho times the integral of x times f of x for the moment about the y-axis. And the moment about the x-axis has rho, the density, times 1/2 f of x squared dx. And of course it goes from one end of the region to the other. Those are the moments. What we're really interested in is finding x bar and y bar. Remember that x bar was equal to m sub y divided by the total mass. So the total mass is equal to rho times the area of the region. So this would be equal to the integral from a to b. I have a rho sitting up here with it. X f of x dx living on top of rho times the area. That cancels. So as long as the density is consistent, then it doesn't matter as far as where the center is, which makes sense. So we have 1 over the area, integral from a to b of x times f of x. Similarly, if we want y bar, it's the moment about the x-axis divided by the mass, which would be rho integral from a to b 1/2 f of x squared divided by rho times the area, because that's the mass. Again, the rows cancel, so this is just 1 over the area integral from a to b 1/2 f of x squared dx. What helps me to memorize this is that x bar has this extra x here. It's just x bar has the x times f of x. And then the y bar is 1/2 of f of x squared. We'll do an example. First, we're going to calculate the moments for this lamina, and I'm going to take a minute and sketch it up. Okay, I sketched my triangle, and I'm assuming that this corner right here is at the origin. And I just plotted the points because it's such an easy line to find the equation of. The slope was the change in the y's divided by the change in the x's, and it's easy to just write it down in y equals mx plus b form. So now I'm going to calculate m sub x and m sub y. M sub x is going to be equal to rho, which in this case is 4. Integral from 0 to 2, and m sub x is the tendency to revolve around the y-axis, so it's 1/2 of minus 3/2 x plus 3 squared. M sub y is equal to rho, the density of the plate, integral from 0 to 2, x times negative 3/2 x plus 3 dx. And I'll take a minute and do that integration and meet you back here. For my moments, I got 12 and 8. I just plugged them in my calculator, even though, yeah, I know they're really easy. I could have done them by hand. Now, I want x bar. That's going to be equal to m sub y divided by rho times the area, the total mass. So let's figure out what the total mass is. Rho times the area. And rho was given to me. It's 4. And the area is 1/2 of the base, which is 2, times the height, which is 3. 2 times 3. So 1/2 cancels with 2, and I end up with 12. So m sub y, which is 12 over rho times area, which is 12. So that's 1. Y bar would be equal to m sub x over 12, and m sub x, oops, I wrote down m sub x for that one. This one would be m sub y, which is 8 over 12, which would be 2/3. And this one's 12 over 12, which is 1. So the center should be at 2/3 and 1. I'm going to plot this in Desmos and see what that looks like. There's my center. They're at 2/3 and 1. Okay. That's just where I went ahead and found the centers of mass already. So let's just memorize those formulas. You're always going to have to find the area first. So those are your steps. Actually, first sketch the region, because you're going to want to know what it looks like. Find the area. And then compute x bar, which is 1 over a times the integral from one end to the other, x times f of x dx, and y bar, which is 1 over a integral from a to b, 1/2 of f of x squared dx. And now I went ahead and found x bar and y bar for that problem. Let's go on to example 4. We want to find the center of mass of a semicircular plate of radius r with uniform density. So, we don't know what the radius is. We're just going to say radius r. I'm going to put the center at the origin, the center of the circle. So my semicircle just lives up here above the x-axis. So if it were an entire circle, it would be x squared plus y squared equals r squared. But since we're above the x-axis, I can say that y is equal to the square root of r squared minus x squared, because it's positive above the x-axis. So I need to know the area. Now you could do the integral from negative r to r of this of y, but why? Because we know what the area of a circle is. It's going to be 1/2 of pi r squared, because it's half the area of a circle with radius r. So x bar is equal to 1 over a. Well, this is pi r squared over 2, so I'm going to write this as 2 over pi r squared. Integral from negative r to r of x times the square root of r squared minus x squared dx. Well, I can do u substitution. U is equal to r squared minus x squared. Du is negative 2x. Dx over minus 2x over minus 2x. And then if I plug in u of r, I get r squared minus r squared, which is 0. If I plug in u of minus r, I get r squared minus negative r squared, which again is 0. So this is equal to 0. Oh, that makes sense because we already talked about symmetry. This thing is symmetric about the y-axis, so its x-coordinate is absolutely, positively going to be 0. We didn't even have to work that hard for it. X bar is 0. Y bar is 1 over a, so I'm going to go ahead and write 2 over pi r squared. Integral from negative r to r, 1/2 of the square root of r squared minus x squared squared. Now I have a 2 here, I'm going to cancel. I have 1 over pi r squared, integral from negative r to r, and when I square this, the radical goes away and I'm really happy. So I have 1 over pi r squared. Antiderivative of r squared is r squared times x minus x cubed over 3, evaluated from minus r to r. So 1 over pi r squared. I have r cubed minus r cubed over 3 minus negative r cubed minus negative r cubed over 3. And when you do the arithmetic on that, I'm just going to scroll down, we get 4r over 3 pi. And there's the pretty picture. Find the centroid of the region bounded by the curves cosine of x and y equals 0, x equals 0, and x equals pi over 2. Step number 1, sketch your graph. So take a minute and do that, and I'll do it too. We're going to pretend like my graph looks like cosine and not just like a quarter circle. You know, cosine goes like that. It should have some change in concavity, but mine doesn't. That's okay. First thing I'm going to do is find my area. I'm going from 0 to pi halves cosine x dx. So that would be sine x evaluated from 0 to pi halves. So that's sine of pi halves minus sine of 0, which is 1. Oh, life is good. So x bar would be equal to 1 over 1. I'll write it down just for completeness. Integral from 0 to pi halves x cosine x dx. Looks like something we would need partial fractions for. not partial fractions, integration by parts. We would need integration by parts. U is equal to x, du is dx, dv is cosine, so v is equal to sine, so we have x sine of x evaluated from 0 to pi halves minus the integral of v du sine of x from 0 to pi halves. So I'm going to go ahead and do my integrating before I plug stuff in. X sine of x minus the antiderivative of sine would be minus negative cosine of x from 0 to pi halves. So I have pi halves times sine of pi halves plus cosine of pi halves, which is 0, minus 0 times sine of 0, which is 0, plus cosine of 0, which is 1. So it's pi halves minus 1 is my x coordinate. Now I need my y coordinate. So y bar is equal to 1 over 1. I'm not even going to bother to write it down this time. Integral from 0 to pi halves, 1/2 of f of x squared. And let's fix that. So it would be 0 to pi halves, 1/2 of 2, 1/2 of 1/2 times 1 plus cosine 2x. And since I'm running out of room, I'm going to go ahead and finish it and turn my paper over. Okay, I had a whole lot of 0 going on in there, but I ended up with pi over 8. So the exact value is pi halves minus 1. Pi over 8 is my center of gravity. Okay, your turn. Find the coordinates of the centroid of the region bounded by square root of x and y equals square root of x and y equals 0. So between the square root and the x-axis, and x equals 4. So you know it's going to be that little area in there. Did you get an answer? First thing I did was I found the area. I took the integral from 0 to 4 of the square root of x. I got 16/3. So 1 over 16/3 is 3 over 16. Integral from 0 to 4 of x to the 3/2 power. I did some plugging and chugging, and I got 12 over 5. Y bar was even easier because we square the square root, and we end up with just the integral of x, and I got 3/4. So my ordered pair is 12 over 5 and 3/4. And I did put it in Desmos to see what it looks like, and it looks like that. Looks good. Looks like the center. Now, if we have the area between two curves, then the formulas are exactly the same. The biggest problem that students have is you have to square the f's and the g's separately. So be sure you have top minus bottom and square your f's and g's separately for your y bar. Now let's look at one. And well, we kind of know what the answer is going to be because I put the answer up there, but we'll go through it anyway. We want to find the centroid of the region bounded by y equals x and y equals x squared. Well, we've used this example a few times. We know that y equals x equals x squared equals x squared minus x equals 0, x times x minus 1. We know that they cross at 0 and 1. So I'll draw myself a little graph just because. So there's my parabola, there's my straight line, and this is the point 1, 1 where they cross. First thing I need is the area. I like to draw the picture so I can see who's on top and who's on bottom. 0 to 1 of x minus x squared, because the line is on top until you get to 1. So this would be x squared over 2 minus x cubed over 3 from 0 to 1, and luckily it's not too hard to do in your head. 1/2 minus 1/3 would be 3 over 6 minus 2 over 6, which is 1 over 6. So x bar would be equal to 1 over a, so 1 over 1/6, integral from 0 to 1 of, and now we have x times f of x minus g of x. X times x minus x squared dx. So 1 over 1/6 is just 6. Integral from 0 to 1 of x squared minus x cubed, which is 6 times x cubed over 3 minus x to the 4th over 4 from 0 to 1, which is 6 times 1/3 minus 1/4. 1/3 would be 4 over 12. 1/4 would be 3 over 12. So 6 times 1 over 12 gives me 1/2. Kind of makes sense. It's kind of symmetric, sort of, there from 0 to 1. And now let's figure out the y coordinate. Y bar, 1 over 1/6 is 6. Integral from 0 to 1, 1/2 of, square them separately, x squared minus x squared squared. 6 times 1/2 is 3. X squared minus x to the 4th. So 3 times x cubed over 3 minus x to the 5th over 5 from 0 to 1. 3 times 1/3 minus 1/5. So we have 5 over 15 minus 3 over 15, which gives me 3 times 2 over 15, which is 2 over 5. So my ordered pair is 1/2, 2/5, and there's the pretty picture of it, 1/2, 2/5. We got exactly what we were supposed to get. Now it's your turn. Y equals 2 minus x squared and y equals x. Go. How'd this one go? Not too bad. The integration's not hard. I admit I didn't do it by hand. I just plugged it in. I found that they cross at -2 and 1. So remember, don't assume everything's in the first quadrant. This goes over 3 quadrants. So my area was 9 over 2 because we do the parabola minus the line, then x times the parabola minus the line, and then y bar 1/2 of the parabola squared minus the line squared. Don't forget to square them separately. And there's the pretty picture. That's the area between those two curves, and that's the center. Memorize the formulas. You won't have any problem with these.